So thank you for coming. I think this is the third talk today about distributed system. So if you look at the agenda, there were already 2 talks this morning about this distributed system. So who attended the earliest 2 talks? Okay, some of you. I just attended the second talk by Tim Berlum. So my talk, the idea of my talk is to give you some knowledge, practical knowledge, to help you to choose correctly which framework, which big data framework or solution that is the best suited for your project, for your requirements. There is no the best solution. It doesn't exist. It depends on the trade-off. And each solution, each framework has pros and cons, right? So let me introduce myself. My name is DuyHai DOAN. I'm working as a technical advocate for DataStax, the company that contributed to Apache Cassandra. So because of my job, I am interested by a lot of distributed systems. So not only Cassandra, but other NoSQL database also. I also contributed to Apache Zeppelin, which is the notebook based on the JVM. So who is from here or who knows Zeppelin here? Raise your hand. So with Zeppelin, you can also connect your notebook to Cassandra, Elasticsearch, Hadoop, whatever. So this is the agenda of my talk. In the first part, I will talk about some theory and properties of distributed system. You need to know them in order to understand all the trade-offs. The second part will deal with how we shard data, how we distribute data, and how we replicate data, and all the issues and the complexity of this distribution and replication. In the third part, I will give a small summary of the CAP theorem. I will not go into detail because we don't have enough time. I can talk for 3 hours on distributed system, but we are limited by time frame. And in the last part, I will compare the 2 major architecture we have right now, master-slave and masterless. So the theory in this distributed system, we start with time. There is no absolute time in theory. Even if you have atomic clock, right? The time drift, you cannot avoid them. You know that Google, they have atomic clock on their server, and they synchronize their atomic clocks with GPS. But even then, they cannot guarantee to have a perfectly 100% synchronized clock, right? So the solution is to have some software to synchronize from time to time your clocks. This is called NTP, right? A well-known software from system operators. But installing NTP is not enough. You need to configure it properly. I have seen a lot of people in production, okay, oh yes, we have installed NTP, but you didn't configure it. So at the end of the day, they have like time drift of 500 milliseconds of time drifts, right? So configure it properly. Because time is not absolute, how can we order operations in a distributed system? What does it mean that one transaction happened before or after another transaction, right? And especially when you have a transaction that can span across multiple continents because you have different data centers. How can it be possible? In fact, it is possible to guarantee a local or relative ordering. If you ship all of your operations, all of your transactions in a single machine, in this case, you can guarantee that on this single machine, you can order your operations, right? Or you can say, okay, let's do a global lock. I will lock all of for each transaction, I will lock all of my machines, and then execute this single transaction, and then release the lock. In this case, yes, you will have total ordering. but the cost is extremely high, right? Because now you have a global lock. To help you with local and partial ordering, there are several algorithms developed in the literature. You have Lamport clock. So the idea is very simple. From the sender point, every time a sender sends a message, it also ships a timestamp. And every time a new message is sent, the timestamp is incremented. Right? So here we call it timestamp. It can be just an integer, right? It's a logical time. From the receiver point of view, every time the receiver receives a message with its timestamp, if you take the maximum of the received timestamp plus and its own timestamp plus 1. So it means that the receiver clock will always be bigger than the sender time. And with this simple algorithm, we can guarantee a partial ordering between a pair of sender-receiver. Right? So this is one known algorithm. We have another algorithm called vector clock. The idea with vector clock is every time you send a message, you assign also a kind of logical time. Right? So you ship, it's a kind of metadata that go along with your data. And at some point in time, if you have multiple inconsistency, vector clock will help you to detect it. So if you have message A with timestamp 4, message B with timestamp 5, and so you know that you are missing message A with timestamp 5, right? So vector clocks will help people detect the inconsistency. You know that there is a problem, but vector clock cannot help you to solve the problem. How can I merge those different values? You don't know. It's up to the developer to know which value is the correct value. Now let's talk about latency. We talk about time, ordering of operation. Let's talk about latency. So the common definition of latency is the time between the moment you send the request and the moment you receive the response. Okay. And the latency is composed of network delay, the time spent in routers and switches, the time spent in DOS, but we can neglect it, and also the time spent to process the query, the request itself. For example, if you are querying a database, your latency will be composed of the time the database takes to read the data from disk, of course. And now if we look at the physics, the speed of light in the void is 300,000 kilometers per second in the void. But in fiber optic cables, it is less than this. It is 197,000 kilometers per second. So it means that if you do a ping between London and New York, you have a server in London, you ping another server in New York. Because of this physics, the ping cannot take less than 56 milliseconds. It's impossible, theoretically, to go under this delay, right? So now, I will ask you the question. If some database vendors say, the average latency of my database is below 10 milliseconds, is it true or is it wrong? Who thinks it is true? Raise your hand. Okay? Who thinks it is wrong? Okay? In fact, there is a trap. It can be true or wrong. Why? It depends on where you take the measure, right? If you measure the latency just next to the machines, of course you can have 10 milliseconds of latency, of course. But if your client, the client which is requesting the database is from New York or from the other side of the earth, it's impossible, so it's wrong. So be careful when you read this kind of marketing material. Say, okay, my database is fast, blah, blah, blah. Ask yourself, how do you get this measure, right? Now let's talk about failure, because in distributed system, there are failures. You cannot choose not to have failures. Failure happen. We have different kind of failures. So from the literature, you have Byzantine failures. It means that you give an input, and the output you expected is wrong. So it can come from application bugs or whatever. Most of the time, it is an application bugs. And then you have also performance failure. It means that you expect the response to arrive in a time frame, but the response arrives too late, or sometimes it doesn't arrive at all. It is the omission failure. So it is a special case of performance failure when you have when you reach the timeout, right? And of course, we have crash failure when the server never responds because it crashed. So in fact, there are only two interesting kind of failure. A value issue. So Byzantine failure, you have an issue with the value you receive, and timing failure. Now, why do we have failure? I will focus more on timing issues. Because sometimes, of course, you have hardware issue. You can have a disk which die in the middle of a process. It can happen. You can have some network packets that are lost. You can have also failure depending on your workload, right? When you are flushing a huge file on the SAN, it may take time because someone else is using the same SAN and for writing a lot of data. If you are using a JVM technology, Java technology, you know that you can have a long GC pause. Like long means it's all relative, but it can from 2 or 3 milliseconds up to 1 second, right? So in fact, from the client point of view, defining failure is hard because when the server doesn't respond, doesn't give you an answer, you don't know what happened. It can be a hardware crash, it can be a long GC. You don't know from the client point of view, of course. So defining failure is hard. And the common definition of failure is, as a developer, as a client, if I send a request and I don't receive an answer in a timeout, it means that it fails. It is a common definition for all developers, right? We all know that. Now, how can we detect failure? Okay, failure is hard to define. We don't know what happened from the server. But how can we know that a server has failed? There are some ideas. Heartbeat. We just ping the server. It doesn't reply. It means it's dead. But the heartbeat is too simple because it's binary state, up, down, right? So we can extend the heartbeat with multi-heartbeat with threshold. So, okay, I ping at least 5 times or 3 times or 10 times, and after 10 times, I say, okay, I decide that this server has died. You can have multi-heartbeat with exponential backoff. So between 2 pings, you wait a little bit longer. You have also other failure detection models, which is based on statistic, right? Complex. So to sum up all this, all those theories, we said that time is not reliable because we don't have absolute time. Global ordering is hard. Failure can happen every time in distributed system. So how can we achieve consensus? How can we take decision in a distributed system? And in the literature, people have defined some important properties to create algorithms to reach consensus. There are 3 important properties. Validity. If you have a distributed system with multiple actors, multiple machines, and if they can reach a consensus, it means that the agreed value must have been proposed by some of the machines, at least one. Validity. Termination, it means that, okay, my algorithm should finish. It should not last forever. Agreement means that if all the machines agree on a value, this value should be the same for everyone. It sounds obvious, but in distributed system, we can have very weird scenario, right? Where the chosen value is not the same. So let's look at known algorithms. So in the past, in the database landscape, we have two-phase commits, okay? The problem with two-phase commit is the coordinator, which manage the transaction. If these machines die, well, your transaction will never finish. So the termination property is not correct. Then people invented three phases commit. They added an extra phase. But there is a problem. In a rare case of network partition, when you can have inconsistent state, how can it happen? So your coordinator will stay on one side of the partition. On the other side, there may be another coordinator elected. And this new coordinator will take decision. And when the network partition disappears, now we have two coordinators, two masters. So who has the right value? We don't know. So we have a problem with agreement property. So to solve all of those issues, people have designed Paxos, Graph, and Zap. So those three protocols, they satisfied all the three properties, right? And the idea of those three protocols is that they are based on a quorum. A quorum is a strict majority. So if you have 5 machines, to be able to reach a consensus in distributed system, you need to have a strict majority on the number of machines. So a strict majority out of 5 is 3, right? So all those algorithm is based on the quorum idea. So it means that every time you read some marketing material and people say, okay, we have some kind of distributed consensus protocol or whatever, leader election, ask the vendor, which of those algorithms are you implementing? Is it Paxos, Graph, or Zap? If they don't implement none of them, those 3, it means that they have invented their own algorithm. Any questions so far before moving forward? No? Okay, let's move forward. Data sharding and replication. So now we focus on your data. Why do we need to shard your data? Because in distributed system, we want to scale out horizontally, right? And the sharding objective is to map a logical part of your data to some physical machines, right? How to shard? There are 2 ways. Some systems allow the user, the developer, to choose their own algorithm to shard. So the user choose their own sharding algorithm, and the columns, so the piece of data on which they apply this algorithm. Some other system imposes the sharding algorithm. The user only decides on which column they want to apply them. So let's take some example. I have a table user. It is a stupid example, but you will understand. I have a table user. I have an email column. An email should be unique for each user, right? I want to shard my data, my user data. So I say, okay, let's take the sharding key. The sharding column is the email address of each user. And my algorithm is, let's just take the first letter of the email address. But obviously, it is not a good sharding algorithm because you have an imbalanced distribution of your data. Okay, fine. So to solve this, some system force you to use the same algorithm, for example, a hash function, murmur-tree or MD5. And the idea is whatever columns, whatever data you choose, they will apply a hash function on this data. And of course, the hash function has been chosen to have a good distribution, right? Now, there's a tricky question. Imagine that I tell you, with murmur-tree or MD5, we are guaranteed to have an even data distribution. Is it true? Raise your hand. Is it wrong? Why is it wrong? Well, it's not totally wrong, but it's not totally true either. All my questions are tricky, because there is a trap always. Let's play a game. So it's not if it's always true, is it wrong? We all know this game, right? You roll dice. You roll dice 100 times. This is the distribution. It's not perfectly balanced. You roll dice 1,000 times, 1,000,000 times. So it's all about statistics. If you apply your hash function to only 10 values, you don't have any guarantee to have a good distribution, right? If you apply the hash function to 1,000,000, 10 million values, now it's better. So again, idea, when you choose your sharding key or sharding column, think about how many distinct values you will have. If you know that you will have only 10 distinct values, it is a bad sharding key, right? But that's not all. So we see that we have two strategies, sharding based on hash and sharding based on user-defined algorithm. The problem with the user-defined algorithm is you can have hotspot, you can have imbalance data distribution. But it allows you to have range query, inequality. For example, give me all the users where images start with A and finish with D, for example. This query, you can have this query because the sharding is a logical sharding, right? You cannot have this kind of range query with a hash-based sharding. Why? Because when you hash your data, you lose the ordering. So you see the trade-off. You choose one logical sharding, you have feature, range query, but you lose on data distribution. You choose hash sharding, you have good data distribution, but you lose on feature. This is the trade-off. So, of course, some NoSQL database, because they are key value store, they choose to have a logical sharding to allow range query. But in this case, they need to solve the problem of data distribution. And one way to solve the problem is to rebalance. Sometime in the documentation, you can see this word rebalance. What does it mean? It means that if you have a logical sharding and sometime your data is not well balanced enough, there will be some process to move your data around so that at the end of the day, all of the shard has an equal amount of data. So this process of rebalancing can be automated or can be a manual process. Okay? But in any case, you need to understand that rebalancing is not free. Rebalancing means copying data. Means you need to read from disk I/O, into memory, transfer on the network, and if you rebalance on your production, it has an impact, right, on your production. So any decision taken in this distributed system has always an impact. Now let's talk about data replication. We know how to distribute data. Now, how can we copy our data? So there are two types of copies. I call replicas or copies the same thing, same vocabulary. You can have symmetric copies, replicas, or asymmetric replicas. For symmetric replica system, when you write data, because there is no role, there is no master or whatever, you can write the data to all the 3 replicas. They are all the same. Right? When you are reading data, you can choose this one, or this one. You can choose one of them, 2 of them, 3 of them to read data from. They are symmetric. You don't care. Now, if you have asymmetric replica, so here I write master, but in some documentation, it is not master, of course. It is primary replica, secondary replica. But the idea is the same. First, the client writes to the primary replica, and then this primary replica is in charge of distributing the write to the other replicas. And the same thing for reading. The client always contacts the primary replica, right? So in this case, we can see that there is a bottleneck, right? Of course. Every operation should go through the primary replica or the master replica or whatever. Right? So some systems, some vendors, some database allow you to skip the master, skip the primary replica when you read data. Instead of going through the primary replica, you can the client can just contact directly one of the replica. But be careful. In this case, when you choose to do that, of course, you have a gain in performance, but you may lose consistency. Let's see. Here I show you 3 common write failure scenarios. They are very classic. The master sends a write request to a replica. The message is lost in the network, so it means that the master will never receive an acknowledgement. So it is the write to this replica is considered to be KO. Right? Second scenario. The replica receives the request, the write request, but because it has a huge load or it has a long GC, the write request is dropped. It's not processed. It's not written to disk. So it means that this replica will never send back an acknowledgement. So from the point of view of the master, the operation has failed. Okay. The last scenario is the replica received the write request, write it to disk, but just before sending back the acknowledgement, it crashes. The process just dies. So it means that from the point of view of the master, the data has not been written. But if you restart this replica, the data is here. Right? Those scenarios are quite common. There's some tricky one. The master sends the write, the replica receives the write to disk, send back the acknowledgement lost in the network. Again, the data is here, but from the point of view of the master, the write has failed. So from the point of view of the master, there is no data on this replica, you see? Another tricky scenario is some database, for performance reason, they choose to write to memory. So the replica receives the write, it puts in memory because it's fast, and then it sends back an acknowledgement. But the write is only in memory, not yet to disk. The master can receive the acknowledgement. It means that, okay, the replica has the data, but what if the replica dies before flushing the data to disk? It means that you don't have the data, even if it has sent back an acknowledgement saying that it is okay. So even with master-slave and primary, secondary shard system, you can have tricky scenario where the slaves say that the data is written, but in fact, nothing is written. Any question for this part, data replication and data distribution? No. Let's move on, the CAP theorem. So who knows a little bit about the CAP theorem? Raise your hand. Okay, few of you. So I will not go into details. I will just do a summary and give you some interesting perspective. So CAP theorem, it has been a conjecture from Brewer, and then it has been demonstrated in a later paper, 2002. The CAP theorem say that in any distributed system, you can have at most two, you can satisfy at most 2 out of 3 properties. Consistency, equivalent to having a single update, up-to-date copy of your data, high availability for update, for write, and tolerance to network partition. But in fact, so a lot of people have shown this famous triangle where you have consistency, availability, partition tolerance, and then they just sort out all the NoSQL database depending on if they are available, partition tolerant, and so on. But it is very simplistic. First, you cannot choose not to be partition tolerant because failure happens. You can have network partition. You cannot choose not to have them. So in fact, you need to support partition tolerance, the P here. But when you don't have network partition, you can try to have consistency and availability, right? Because there is no network partition. And if, not if, when partition occurs, you choose your side. Either you give up on availability and you choose consistency, or you give up on consistency and you choose availability. So it gives us some notions of tunable consistency. It means that the level of consistency, you can choose them. So what is consistency? What is the definition of consistency? In fact, it is very complex. The consistency, the C of consistency of the CAP theorem is different from the C of ACID, right? Atomicity, consistency, isolation, durability. ACID of relational database. On this diagram, you can see a lots of different levels of consistency in the literature of distributed system. Read uncommitted, read committed, cursor stability, and so on. Of course, the highest level is serializability. You can see there is a green block and a red block. All the consistency level in the green blocks don't require coordination. All the consistency level in the red block, because they provide more consistency, they require coordination. What do we mean coordination? We mean distributed consensus. Remember the 3 algorithms I mentioned, Paxos, Raft, and Zab. If some database or some distributed system say that it guarantees snapshot isolation or linearizability, it means that necessarily they have to implement Paxos, Zap, or Raft. Otherwise, there is a problem. So let's take an example of Cassandra because I know Cassandra very well. In Cassandra, you can choose to execute your query with consistency level 1. It corresponds to read committed. If you want something a little bit stronger, consistency level quorum, which require a strict majority of replica to reply to your request, it corresponds to read your write. If you want something even stronger, in Cassandra you have lightweight transaction, they call lightweight transaction. It corresponds to single partition linearizable writes. So your writes can be linearized, but only in a single partition, so on a single shard. You cannot have multi-shard linearizable write because it will require a distributed lock, and it's very expensive already. Right? So we talk about partition tolerance, easy, consistency. Now, what about availability? Is it an availability to read in case of failure or to write in case of failure? So from the strict definition in the paper, in the original paper, the high availability of the data is only for update, only for write. But in practice, as a developer, if my database is only available for write, but not for read, not very useful, right? Let's take another example. Cassandra claims to be highly available because it is an AP database according to the CAP theorem. Some marketing slides even claim continuous availability, like almost 100% availability. Is it true? Let me give you some example. Here I have a cluster of 1, 2, 3, 4, 6, 10 machines. The yellow color means I have 3 copies of my data on the cluster. And I have a network partition. If my client connects to the left side of the partition and is requesting for some data for reading, give me the data. With consistency level 1, it means just contacting 1 replica out of 3, I can satisfy the request because I have my replica here. But this scenario is very optimistic because I'm lucky. What if I have this kind of network partition and all of my replicas belongs to the other side of the partition? In this case, my request will fail because I don't have any copy of my data from this network side of the partition, right? So in this case, I don't have high availability. So how is it possible that some marketing slide claims Cassandra to have continuous availability? In fact, there's a trick. The trick is if you have 2 data centers set up, right? So you should know that in Cassandra, when you have another data center, 100% of your data are copied to the other data center, plus all the replicas. So if you have a multi-data center setup, and only if in this scenario, we have a network partition from the European data center, the client, the driver, can switch automatically to the other data center to read the data. And only in this scenario, you can have almost 100% high availability. So the high availability, the continuous availability, is not given by the AP property of CAP theorem. It is given by the multi-data center support. So be careful with marketing claims, right? If you have a single data center, you will never have continuous availability, sorry. Any question for the CAP theorem part? No? Clear? Now let's finish with architecture. Master-slave compared to masterless. So we have pure master-slave architecture. A single server will take care of all the operation write and read. The advantage of that is because every operation goes through a single machine. Remember, at the beginning, I was talking about global ordering. In this case, it is possible. You can serialize all your operation because you have a single master. It is easy to reason about. And you can even have pre-aggregation. It means that you can pre-compute the minimum, the average, the maximum values of your data. Because everything goes through the same machines. Of course, the drawback is you cannot scale, right? On write. And you have a single point of failure. So to solve those drawbacks, so you see this kind of, people introduced the multi-master slave architecture. How does it work? So it is divide and conquer. Now, instead of having a giant single master in my system, I split my system in shards, so data distribution. And for each shard, I have a master of the shard, so the primary shard, and secondary shard, which correspond to the slave. And now, every write will go to the primary shard first, and then dispatch to the secondary shards. The advantage, of course, is now you have no longer a big single point of failure. You can still order your operation inside a single shard, inside one shard. You can serialize them. But now you can no longer have global ordering, of course, unless you have a global lock, of course. Sometimes I can read this kind of objection. I said, okay, but in case of failure of a master or primary shard, you need a master election, and it takes time. And the database vendor tell me, but okay, don't worry. It takes only 10 milliseconds to elect a slave into a master. But in fact, I don't care that it takes 10 milliseconds. What is important is how long does it take me to detect that one master is down. You have two times here. The time it takes to detect that the master or the primary shard is down, and the time to elect a new primary shard. And in fact, the bigger time is on the left. Remember when I talk about failure detection, how can you detect failure? Simple heartbeat, multi-heartbeat with threshold, or multi-heartbeat with exponential backoff. All those algorithms, simple heartbeat is eliminated because it's too simple. So usually in production, people use multi-heartbeat with exponential backoff. And the time to reach the timeout is in seconds, not milliseconds. Right? So what is important is the time to detect that the master is down. This is the biggest time. And during this time, your system is not available because you write come-ins, but you don't know if it has been successful because the primary shard doesn't answer. Oh, we have also another funny stuff, fake masterless shared noting architecture. In fact, those solutions are multi-master architecture, but they are branded as shared noting, masterless. This is me. Look at the date. It was December last year. So I have seen a new NoSQL database. I read their document online. They said, truly masterless. And then in another chapter, they said, master node election. There is a contradiction, right? So if you are masterless, why do you have a master node election? It doesn't make sense. So I ping them, say, hey, there is a problem in your documentation. Oh, okay. We will update it. It was in December last year. I checked the same website last month this year. Masterless architecture, blah, 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 blah. Perfect. You see this link? Technical overview. Click on the link. What can we see? Writing data. When you write the data, the operation is routed to the primary shard for execution. If the operation gets executed on the primary shard, it will be pushed to all the replicas. Do you remember this? This is a multi-master architecture. So be very careful. Every time you see masterless shared noting architecture, ask for the details. How are the writes written on the replica? Does it go through the single replica first, or does it go through all the replica? And then you will get your answer. Let's finish with masterless architecture. Of course, in this case, you don't have master, so every node has equal role. But it's not perfect either. Now, how can you manage inconsistency? Because you don't have any master, so you don't know which value is the correct value, right? So in the literature, we have some data structure to help you. We have vector clock to help you to detect inconsistency. We have CRDT. Who knows about CRDT here? Almost 1, 2, 3 people. OK. I don't have time to expand on CRDT. If you want to know more about this, you can read the paper. So all those data structures help to make your data converge if there are inconsistency. When, for example, I take the case of Cassandra, when you write to a Cassandra cluster, the client will send the request to a coordinator. So it is not a master or whatever, or a kind of primary shard or whatever. It is just the machine which receives your request, and it acts as a network proxy. It will push your data to the correct replica in parallel. So the question people ask me is, what if the coordinator dies? What if this machine goes offline? Well, I can choose another machine. Everyone can be coordinator because it's totally symmetric, right? So I don't care if one machine goes offline. I don't have any master election going on. So this is cool. But now, if I have inconsistency between different replicas, I have problems. So to solve the inconsistency between the different replicas, Cassandra proposed an algorithm, last write win, based on timestamp. It means that every time you write a data, as Cassandra will assign a timestamp to your data, and the latest written data is the correct value. OK, the idea seems to be simple. But I said before that time is not reliable, right? OK. So now, why did Cassandra choose this kind of algorithm if time is not reliable? In fact, it is a practical choice, because last write win is pretty intuitive. It's very easy to explain to people. You don't need to understand CRDT. You don't need to read all the research paper to start using Cassandra. But the trade-off is, the drawback is, it opens the box to some weird issue. So let me show you some things. Imagine you have a user with some age, and you update the age. Update user set age equals to 32, where user ID is 1. So you update the age to 32. The update request comes to the coordinator here first. And the local time of the coordinator is 10 o'clock, 1 second, 50 milliseconds. So now, on each replica, the age 32 is written with this timestamp. OK, fine. Imagine that a little bit later, very fast, another client will update the age to 33. But this time, the client contacts this coordinator. And here, you can see that there is a time drift. The local time is not perfectly synchronized. It is in the past a little bit, 20 milliseconds. So now my new value, 33, will be written with 20 milliseconds in the past. And now if I read, give me select age from user ID 1, Cassandra will give me 32 and not 33 because of the timestamp, right? So when you are using Cassandra, you should know about this. So how can you cope with this? First, it's quite rare to have an update on the same column, on the same user, by different client, almost at the same time. But if you have this requirement, if you have this functional requirement to be able to update them, you can use lightweight transaction, right, which guarantee linearizable writes. But it is very expensive for network round trips. See? So when you choose a masterless architecture, you have always also trade-off. It is not free. It is not magic. To sum up, advantage, no single point of failure, no failover procedure. You can lose a machine, you don't care. They are all symmetric. You can have almost zero downtime if you have a multi-data center setup. The drawback is the consistency model is really hard to reason about. And it is very expensive if you want to have very strong consistency. Right. Question?
I have a question about this slide when you show that you read your own write, the correspondence with.
Okay, this slide. So the question is, he wants to see the slide when I said read your own write, consistency level quorum.
So to achieve this, you have to write with consistency level quorum, but also read with
Yes. Yes, I simplify a little bit, but the remark is to achieve if you want to be able to read your own write, and he's perfectly right, you need to write at quorum and read at quorum also. Because when you write at quorum and you read at quorum, you contact away a strict majority. So even if you lose some machine, you are sure that there is at least one machine that sees all the operations. You are right. I didn't go into the detail because it's not the purpose of this presentation. Other question?
Do you provide the slides?
The slide will be put online, yes. Other question? Okay. Thank you.